Good evening, students. Welcome to 11th physics. Okay. So today chapter name work energy power. Okay. Work work energy power. And the topic name is the potential energy of a spring. Okay. Right. So before we dive into the class, let me show one picture. So this is motivational segment. So here you can see one picture. Hidden today, power tomorrow. Yeah. Now take a look at the image. This is Robert Hooke, a brilliant scientist from the 17th century. Near his name, you will see a Latin phrase "Attentio service." In simple English, it means as the extension, so is the force. Okay, as the extension, so is the force. Hooke discovered Hooke's law of elasticity. He proved that the more you stretch or compress a spring, the more force it pushes back with. Okay, the more you stretch or compress a spring, the more force it pushes back with. Okay, but today we are not just studying physics, we are studying the physics of your life and your potential. Now focus on the center. Look at the center. Okay, so look at this giant spring. When a heavy downward force, a big pressure is applied. What happens when heavy downward force, a big pressure applied? What happens? The spring compresses. Yeah, it gets pushed down. It looks small, trapped, and restricted. But chemically and physically, what is actually happening inside? Energy is being stored. Okay, energy is being stored. When that heavy force is finally removed, the spring does not just sit there. Yeah, already you know that. It snaps back and with incredible speed. That means energy is released. So when the heavy force is finally removed, the spring does not just sit there. It snaps back with the incredible speed. Energy is released. Think about that heavy boulder. This person is pushing at the bottom. Right now, you might feel like you are under a massive rock. You might feel the weight of the exams, personal struggles, or fear of the future. But remember this first right here: stress today, strength tomorrow. The pressure you feel right now is not destroying you, it is gathering power inside you. Okay, so remember that. The four life lessons, focus on the right column. Let's break down exactly what this means for your daily mindset. Look at these four symbols on the right. The weightlifter. Every challenge builds your inner strength. You don't get strong muscles by lifting light feathers. You get strong by lifting heavy weights. That make you sweet. Your struggles are your training ground. Okay. And the second one, the mountain. Every setback prepares you for the comeback. When you fall down a mountain, it just gives you a clearer view of the peak you are about to climb. Third one, the plant sprout. You may be compressed now, but you are not defeated. A seed must be buried in total darkness and pressed under heavy dirt before it can break through and grow into a massive tree. So you are in the dirt phase right now. Keep growing. And the fourth one, the rockets. At the right moment, you will bounce back stronger than ever, like a rocket built to withstand extreme atmospheric pressure. You are engineered to break through barriers. Clear? Okay. So the final charge. Focus on the bottom text. So class, look at the main headline. Hidden today, power tomorrow. People might not see your hard work right now, but they might only see you struggling or staying up late studying. Your power feels hidden, but it is there. It is storing up. Never forget the final reminder at the bottom of the board. Your potential is real. Keep trusting the process. So when you feel compressed this week, smile. Remember Hooke's law. Remember the swing. You are just storing up the energy to launch yourself higher than you have ever gone before. Okay. Now let's get to work. So before we entering into the topic, we'll share the 3 MCQ. 3 MCQ. Here you can see the 3 MCQ. So you can type the answer in the chat box. First question. What is the SI unit of work done or energy? What is the SI unit of work done or energy? What is the SI unit? Newton, watt, joule, Pascal. SI unit of work done or energy. Very good. So work done or energy? Okay. SI unit of work done or energy? Answer is very good. Joule. Option C. What happens to the potential energy of the object when it is lifted to a height h against gravity? So you lift the object or ball to the height h against the gravity. So what happens to the potential energy? Decreases or increases or remains zero or it becomes infinite? Which one is correct? Which one is correct? Potential energy. So already you knew about the formula of potential energy. Yeah, U is equal to m g mg h. Very good. So mg h. So height increases, potential energy also increases. Very good. So increases. Third one. According to the work energy theorem, already know about that. So work is equal to change in the kinetic energy or change in the energy of the system. So this is the work energy theorem. The net work done on the object is equal to the change in its potential energy, kinetic energy, total acceleration, linear momentum. The net work done on the object is equal to the change in it is potential energy, kinetic energy, total acceleration, or linear momentum. Yes, very good. Kinetic energy. Yes. So let me check the answer. What is the SI unit of work done or energy? Joule. What happens to the potential energy of the object when it is lifted to the height h increases? According to the work energy theorem, the net work done on the object is equal to the change in its kinetic energy. Yes, good, super. Now, let me show the concept. I will share the screen again to show the simulation. So, potential energy of the spring. Potential energy of the spring. Okay. So, here you can see that. Clear? Okay. So, now look at that initial setup. So, before we begin, I want you to think about the something simple. A rubber band. Okay. A rubber band. When you stretch it and let go, it snaps back. Yeah. When you compress a spring in a pen and release it, the pen cap flies off. Yeah. Where does that energy comes from? Where does the energy come from? When you compress a spring in a pen and release it, the pen cap flies off. Yeah. Rubber band. When you stretch it and let go, it snaps back. So where does that energy come from? It was stored. Okay. It was stored. Stored inside the spring itself. What we call potential energy. It was stored. So stored inside the spring itself as what we call potential energy. So today we are going to understand exactly how much energy gets stored. How much energy gets stored. Why it depends on displacement and how it exchanges with the kinetic energy during motion. Okay. So this is your section of 5.9 of your NCERT textbook. Okay. So by the end of the today's class, you will be able to derive everything on the screen from first principles. Okay. Okay. So look at the setup. We have a block attached to the light spring. The other end is fixed. Here you can say that. The other end is fixed to a rigid wall. The surface is smooth. No friction. Okay. Right. So now when the block is right here at the center, this is called the equilibrium position. The block is right here at the center. This is called the equilibrium position. No force acts on the block. Here you can see any force acting on that? No. No force acting on the block. That's why that block is at that center. That means it is in the equilibrium position. The spring is neither stretched nor compressed. Displacement x is equal to 0. Here you can see that displacement. Here you can see that displacement x is equal to 0. Right? Okay. So the equilibrium position is the origin line. Okay. Here you can see that the dotted line marks x is equal to 0. So everything is measured from here. Okay. Everything is measured from here. Now what happens when I push the block to the right? What happens when I push the block to the right? The spring stretches. What happens when I push it to the left? The spring compresses. So in both cases, the spring pushes back. Correct? In both cases, the spring pushes back. This restoring behavior is described by Hooke's law. Okay, this restoring behavior described by Hooke's law. Okay, so here you can see that one formula. F is equal to minus kx. Fs equal to minus kx. Swing force. Fs means already you know that. Fs. Swing force minus kx. So here negative sign is very crucial. Very important. Okay. It tells us the force is always opposite to displacement. Force is always opposite to displacement, because when you pull the spring, displacement opposite to the direction of force. When you compress the spring, it displaces the spring to the opposite side of the compressed force. Yeah. So force is always opposite to the displacement, or in other words, displacement is opposite to the force, applied force. Okay. So if x is positive, the block moved right. Yeah, here you can set positive value. X is equal to, yeah, x is equal to positive value. So if x is positive, block moved right. You can see that. Force is negative. Force is negative. Spring pulls it left. If x is negative, block moved left because displacement from the equilibrium position. So it shows that if minus 0.4 meter means from the equilibrium position, we have to measure in the negative direction, negative x-axis, whatever you can take. Okay. So if x is negative, block moved left, force is positive. Force is positive. Spring pushes it right. Yeah. Here you can say that. Spring pushes it right. This is why it is called a restoring force. So this is why it is called restoring force. Now I will drag the x slider to plus 0.4 meter. You can see that. Okay. So here you can see that plus 0.40 meter. Now look at that red force arrow. Red force arrow, Fs, minus 160 Newton, negative direction. Yeah. So notice the red arrow, that is a swing force, Fs. It points left. Is it clear? It points left, opposing the rightward displacement. Opposing the rightward displacement. The longer the arrow, the larger the force. Okay. Remember that. The longer the arrow, the larger the force. Now I will drag the x to minus 0.40 meter. Yes. Now you can see that displacement minus 0.40 meter. Now look at the red arrow. Arrow flips right. Yes. And the value plus 160. Plus 160. So it points right. Always opposing. Always restoring. Is it clear? Okay. Now, spring constant, K. The constant K in the Hooke's law is called the spring constant, and its unit is Newton per meter. Newtons per meter. Okay. So it tells us how stiff the spring is. It tells us how stiff the spring is. Okay. Okay. Let me show you. First of all, let x is equal to 0. Drag the x slider to the 0. Like that. So I will increase or decrease the spring constant, whatever the value we can take. So now I increase the K slider to like that 400 nanometer, Newton per meter. Okay, 400 Newton per meter. So now I have doubled the spring constant to 400 Newton per meter. So this is a stiffer spring. Okay, now you can see that spring constant value only 65.55 Newton for this displacement for this spring constant. Okay, right? Now I will here you can note that value 160 displacement. Now I will decrease the spring constant value 400 to 200. Yes. So spring constant 200. Now you can see that value of spring force only 80. So it has a spring constant. When I take spring constant 400 nano Newton per meter, the spring force 160. Now spring constant 200 Newton per meter, the spring force divided by 2. So 160 divided by 2, 80. Yeah. Okay. So same displacement. For example, you can take the minus 0.40 meter or plus 0.40 meter. Same displacement, but look at the force value in that live values panel. It is now 80 Newton instead of 160. So double the stiffness, double the force. For 200 Newton per meter spring constant, 80. For 400 Newton per meter spring constant, spring force, 160. So double the stiffness, double the force. That is Hooke's law in action. That is Hooke's law in action. Okay, that is Hooke's law in action. So now bring back to the spring constant to 100. 100. Now you can see that, yes, 40 Newton. Okay, so a larger K means stiff spring. Okay, a larger K means stiff spring. Small K means soft spring. Underline that word. A larger K means stiff spring. Small K means soft spring. Remember this. It will matter when we talk about the oscillation speed. Okay. Right. Now, so now what done by the spring force? Now here is an important question for this chapter. How much work does the spring force do when the block moves? How much work does the spring force do when the block moves? So this is not a constant force. F is equal to minus kx, keep changing as x changes. So we cannot use W is equal to F dot D directly. We must integrate. If the block is pulled from the equilibrium position, x is equal to 0 to the maximum displacement xm, the work done by the spring force W. Okay. W is equal to integration of Fx Fs into dx. Okay, Fs into dx. So integration initial point 0 and final point maximum displacement xm. So Fs dot dx, we have to put the minus kx in the place of Fs. So integral 0 to xm minus kx dx. So k is the constant and minus also out of the integral, and x dot dx. Integration of x dot ds gives x square by 2. So here we have to put the xm. So xm minus half k xm square by 2. Okay, minus half k xm square. Clear? Minus half k xm square. So this is what done by the swing force. So the negative sign tells us the swing force opposes the pulling. It does negative work on the block during stretching. Okay. Conversely, the external agent pulling the block, do the positive work. That is plus half kx xm square. Clear? Okay. So negative sign tells us a swing force opposite the pulling. It does the negative work on the block during the stretching. Conversely, the external agent pulling the block, do the positive work plus positive xm square. Now look at the energy bar graph panel. Energy bar graph panel. The positive work done by you, the external agent, gets stored. It does not vanish. Okay. So it is stored as a potential energy in the swing. That is exactly what we see in the potential energy bar right here. So now I will put the x is equal to 0, and from that move the x slider slowly from 0 to 0.4 meter. Watch the potential graph, potential energy bar graph. Yes. So x slider slowly move from the 0 to 0.4 meter. Watch the purple bar, the potential energy. As I increase displacement, it grows. Yeah. As I increase displacement, it grows. And notice the formula in the live values. P is equal to half kx square. Here you can say that. P is equal to half kx square. The energy stored keeps increasing as x increases. The energy stored keeps increasing as x increases. So this is not linear, it is quadratic. Double the displacement, 4 times the potential energy. Okay, double the displacement, 4 times the potential energy. Now x is equal to 0.2 meter. 0.2 meter. Okay, you can see that potential energy bar 2 joule, because half into k square, k 100 Newton per meter, and x 0.2 meter. So we have to square that value and we will get that 2 joule. Then x is equal to 0.4. 0.4. Now you can see that 8 joule. So that is potential energy is 4 times larger. Yeah, potential energy 4 times larger. For x is equal to 0.20 for the given spring constant 100 Newton per meter, the potential energy just 2. But when we double the displacement 0.2 to 0.4, potential energy not changing with linear. That means it does not doubled. Yeah. So it is 4 times larger. 4 times larger. Okay. Right. So now what done is path independent. So now here is a beautiful result from your textbook. You can see that equations. If the block is pulled out to the xm, that is maximum position, then pushed back like here. completing a full circle. Okay, this is a full cycle. So you can see here. You can see here the three dots, energy dots. Purple color potential energy, orange color kinetic energy, and green color total energy. The total work done by the spring force is WS is equal to half kxi square minus half kx square minus half kx square equal to 0 for the full circle. So the spring force does zero network in a complete cycle. Yeah, the spring force does zero network in a complete cycle. So this is a defining property of the conservative force. The work depends only on the initial and final position, not on the path taken. This is why we can define the potential energy for the spring. So now potential energy of the spring. Okay. So we define the potential energy V of x of the spring block system as 0 at the equilibrium position. X is equal to 0. Okay, x is equal to 0. Then for any displacement x, the potential energy V of x of kx square. This is equation 5.19 in your NCERT book. Notice it always positive or 0, whether the spring is stretched or compressed. It is symmetric. V of positive x equal to V of minus x, negative x. Same potential energy for same magnitude of displacement in either direction. It is quadratic, parabolic shape. You can also verify minus dv by dx equal to minus kx is equal to fs. So the spring force is a negative derivative of the potential energy. This is a fundamental relationship between the conservative forces and potential energy. Clear? Okay. Now look at that energy displacement figure. Okay. So this is a figure 5.8 from your textbook drawn live. The purple parabola is P, that is potential energy, half kx square. It opens upward. The minimum is at x is equal to 0. That is equilibrium position. Yeah, it opens upward. The energy stored increases as the block moves away from the center in either direction. The minimum is at x is equal to 0, equilibrium position. The energy stored increases as the block moves away from the center in either direction. So now we come to the most beautiful part. What happens when the block is released from XM, okay, and oscillate freely. Yeah. So at the moment of release from X is equal to XM, the block is at rest, velocity is 0. So kinetic energy is 0. So all the energy is potential energy. So potential energy E total half kx square m. Okay, kx square m. Total energy. Here you can see that. As the block moves towards the center, the spring force accelerates. So potential energy converted into kinetic energy. At the x is equal to 0, the equilibrium position, all the potential energy has become kinetic energy. So the block has maximum speed. Okay, the block has maximum speed. Then it overshoots, compresses the spring, and the kinetic energy converts back to the potential energy. So this cycle continues indefinitely on a frictionless surface. Clear? Okay. So watch all the three bars simultaneously: purple PE, orange KE, green total energy. all the extreme rights. Sorry, at the extreme right, potential energy is maximum, kinetic energy is 0. Yeah. At the center, Ke is maximum, P is 0 at the center. At the extreme right, potential energy maximum. At the extreme left, potential energy is maximum again, K is 0. Yeah, at the extreme left, you can see that potential energy is maximum, again K is 0. And the green total energy bar, it never changes. So this is the law of conservation of mechanical energy. Okay, right. So here you can see that the chart. Once the chart, on the chart, you can see that the purple parabola is PE, the orange is KE, the green dashed line is total energy. Yeah, in the charts, you can see that. At any position of X, if you add the height of the purple curve and the orange curve, you always get the green line. Okay, at any position X, if you add the height of the purple curve and the orange curve, you always get the green line. Always. That is conservation. Clear? Okay. So maximum velocity formula. From the conservation formula equation, half kx square m equal to half kx square plus half m square. At x is equal to 0, ke is maximum and potential energy is 0. Yeah, already you know that. At x is equal to 0, kinetic energy is maximum and potential energy is 0. So we have to put potential energy 0. So then we will get half mv square m equal to half kx square m. So then finally we get pm, that is maximum velocity, root of k by m into xm. Okay. So here you can see that maximum speed, root of k by m into xm. So now set k is equal to 200. 200 Newton per meter. M, we can take as a 1 kg. XM, 0.4 meter. 0.4 meter. Note that maximum velocity. Maximum velocity 5.657. 5.657. So the line live values panel source VM is equal to root of 200 by 1 because K 200 M 1 into XM. XM 0.4. So which will give 5.657 meter per second. Let us check. Okay, let us check. Okay, right. So when the block passes x is equal to 0, point to velocity arrow and the velocity readout. When the block passes x is equal to 0, find out the velocity arrow and the velocity value readout here. So when the block crosses the equilibrium, the orange velocity arrow is longest and the readout shows a maximum v. When the block crosses the equilibrium, the orange velocity arrow is longest and the readout shows a maximum v. So matching perfectly. So let us explore what happens if I increase the mass. So suppose if I increase the mass to 3 kg here. Now we can see that the maximum speed value 3.2666. Yeah. So mass went from 1 kg to 3 kg. Vm dropped from 5.627 like that, yeah, to 3.266 meter per second. So heavier the block, harder to accelerate. So lower maximum speed. Heavier the block, harder to accelerate, lower maximum speed. Makes physical sense. Now what if I increase the spin constant? So now I will bring back to the M to 1 kg. 1 kg. Now increase the spin constant to 400 Newton per meter. So K double to 400 Newton per meter. And Vm now look at that 8 meter per second. Stiffer spin stores more energy and releases it faster, higher maximum speed. Stiffer spin stores more energy and releases it faster, higher maximum speed. And what about amplitude? Now I will increase the XM to 0.8 meter. 0.80 meter. So amplitude double to 0.8 meter. So maximum velocity is doubled to 16. Yeah. So maximum velocity is 16 meter per second because Vm is directly proportional to Xm. Vm is directly proportional to Xm. And total energy is quadrupled because total energy is of Kx square M, which is quadratic in Xm. So here you can see that values. So now I will reset all the values to default. K is equal to 200 Newton per meter. M is equal to 1. X is equal to 0.40. Meter. Okay. And run the animation. So let me summarize everything we covered today. While you watching the animation, 1. The spring force follows Hooke's law. F is equal to minus Kx. It is a variable conservative restoring force. 2. Because it is conservative, the work done depends only on the initial and final position, not the path. A complete cycle gives zero network. A complete cycle gives zero network. 3. The potential energy stored in a swing at the displacement x is equal to Vx equal to half kx square. It is always positive, always symmetric, and parabolic. 3. The potential energy stored in a spring at a displacement x is equal to Vx. V of x is equal to half kx square. It is always positive, always symmetric, and parabolic. 4. The total mechanical energy E is equal to half kx square m is constant throughout the motion. Ke and potential energy continuously exchange, but their sum never changes. But their sum never changes. 5. Maximum speed occurs at x is equal to 0. Yeah, maximum speed occurs at x is equal to 0. Vm is equal to root of k by m, xm. It increases with kx. With increases with k. Okay. Decreases with m. And it is directly proportional to the amplitude. Maximum speed occurs at x is equal to 0. Vm is equal to root of k by m by into xm. So it increases with k, decreases with m, and is directly proportional to the amplitude. Clear? Okay. Now let me show the summary point. and homework. So Hooke's law, F is equal to minus Kx. Okay, F is equal to minus Kx. Second point, work done by the spring. Ws is equal to half Kxi square minus half Kxf square. Work done, Ws is equal to 0 for the full cycle. Yeah. And potential energy of the spring, V of x is equal to half Kx square. Total mechanical energy is conserved. E is equal to half Kx square plus half Me square, which gives half Kxm square. Yes. Maximum speed at x is equal to 0. Vm is equal to root of K by M xm. So this is a summary points. Already I told you. So this is your homework. Verify mathematically that dv minus dv by dx gives the swing force Fs using V of s equal to half Kx square. Second one, a swing is compressed by 2 centimeter, storing energy V. Calculate the ratio of potential energy stored when it is compressed by 6 centimeter. So try this. Okay. Verify mathematically that minus dv by dx gives the swing force Fs using V of x half Kx square. A spring is compressed by 2 centimeter, storing energy V. Calculate the ratio of potential energy stored when it is compressed by 6 centimeter. Okay. So that's all for today. So if you have any doubt, you can ask me in the chat box. I will explain. I will even again show the simulation, spring or calculations. Okay, no doubt. Okay. So thank you, students. Thank you. Jai Bharat, Jai Hind, Jai Vidyasati. Thank you.